Howdy and welcome back. So how does a function know where to find its activation record? What we're going to see here is that there's going to be this thing called a stack pointer, which is going to point to kind of where this line between the stack and empty space is. So this will point to the base of the stack. You can think about, if we kind of think about the stack as an array of activation records, the stack pointer is going to point to the activation record on top. So as we were to maybe step through this example, the stack pointer would point to the base of main, the base of factorial, the base of factorial of 2, base of factorial 1. And the question then becomes, well, how does this help us determine, where, say, factorial of 1's activation record is when we're executing code for the instance of factorial of 1? Well, let me scroll back down here. It's too far. So how does a function know where to find its activation record? When a function such as main calls another function, such as factorial in our example, an activation record for the called function is going to be pushed onto the stack. So what does that actually mean? Well, it means memory is going to be allocated for that function's activation record, where we can store its local variables, parameters, and that housekeeping information that we kind of alluded to in passing. So the stack pointer is going to be moved in one direction to allocate stack memory for that activation record. And that's what I was trying to kind of allude at here. We start out, with, okay, here's kind of the current state of the stack. When we start up our application, there's one activation record on it for main. So the stack pointer is going to, let me go ahead and move this up for consistency. It's going to point to main, it's activation record. And as we add on to the stack, as activation records are pointed onto it, that stack pointer is going to move up. How much is it going to move up? Enough to allocate space for the particular function who we're creating an activation record for's size of that function's stack frame or activation record. Okay, so that's the allocation. What happens when the function finishes execution? Well, the stack pointer is going to be moved back into the other direction and memory is going to be deallocated. So let's just run through a simple, example with the same simple application we were working with, but a bit of a different diagram, which is maybe more informative. We can see here that, okay, we've launched up our program and an activation record for main, shown in the lighter green color here, has been pushed onto the stack. Well, what does that activation record need to store? Well, if we look at main, there's one local variable, no parameters. So it needs to at least be able to store a single integer object, in this case, result. Now, notice here the stack pointer is kind of pointing to the first object stored within that activation record. You can think about each activation record as a heterogeneous array whose elements can kind of be different types of objects. So you might have, in this case, like an integer, and then maybe we had a double in main. Well, we'd have to have space for that double. So, the activation record would contain both an integer and a double, which is, those entities aren't homogeneous. Anyways, we'll get into how we can use the stack pointer later on, I believe in the next lesson, to actually get into a particular activation record and begin interpreting the bits of it according to some sort of base type to say to pull out result or pull out maybe some other object that is residing into it. But anywho, we can see here that, okay, space was allocated. The stack pointer moved up from whatever address it had started out with, and we'll begin running through this. So we hit that function call. Execution of main will be paused. We'll transition into the definition for factorial, which resides in the code static region. And then we need memory for its local variables and parameters. So an activation record is pushed onto the stack. We can see here that that stack pointer has moved, and it is now pointing to the base of factorial of 3's activation record. What does that mean? Well, if we know where that activation record starts, we can actually get into it and begin pulling out the various things that are stored within it. So continuing down, we're kind of not at the base case here. What happens? We invoke factorial of 2. So again, we pause our execution of factorial of 3, transition into factorial of 2, which prompts an additional activation record to be pushed onto the stack. That is done by incrementing the stack pointer in a manner that allocates enough space for that new activation record for factor of 2. We begin executing. We see, hey, we're not at the base case. We have to make another function call. And in that case, we pause execution of factorial of 2, move into factorial of 1, and a additional activation record for factorial of 1 is pushed onto the stack. So at this case, we're at the point where we can begin unwinding the stack. The reason being is factorial of 1, in this case, n, is equal to the value of 1, which is a condition for our base case, meaning this function will simply return with the integer value of 1. So at this point, memory is going to be deallocated by moving the stack pointer back in the opposite direction. So if we look here, we've now finished our execution of factorial of 1, and we're now picked up back where we left off, which is here, in factorial of 2. So notice here, because initially this was factorial of 1, we now have that value returned, which would be 1. And now we can multiply it by 1 by n in this case, which is 2, and return that. But anyways, notice that when the stack pointer moves down, memory is deallocated for the activation record of factorial of 1. C++ does no zeroing out of memory, which means that this activation record is kind of still there, in the sense you could access that object storing 1, but the problem is that the second a new activation record is pushed onto the stack, if it goes at this point, if we were to call another function, that space would be consumed and essentially reallocated, if you will, for something else. In that case, this memory would no longer store what it used to for factorial of 1. So again, all I'm trying to point out here is memory is deallocated, but it's not zeroed out. But for all intents and purposes, please think about this as such. Assume that the memory was truly zeroed out and deallocated, and just think about the stack as now looking like this. So again, we were able to pick up from where we left off here. We're now going to return n, so in this case 2, multiplied by the return result of factorial of 1, and we'll return back to factorial of 3. And we get back there to its activation record by decrementing the stack pointer, and therefore deallocating the memory that had been allocated to the activation record of factorial of 2. So at this point, I believe we've returned to this function. So now we have the value of factorial. We're right here. We're picking up again where we left off. So in factorial of 3, we called factorial of 2, which would have returned the integer value of 2, and we can multiply that by 3. We're at the return case, so we can go ahead and return the value of 6 to the caller, in this case main. And again, memory is deallocated after that return statement, and the stack pointer is decremented to point to the current function's activation record, in this case main. And at this point we have the value for factorial of 3, and this variable here would take on the integer value of 6. In other words, factorial of 3. So how does a function know where to find its activation record? When a function is invoked, the stack pointer is moved in one direction to allocate stack memory for the parameters and local variables associated with that instance of the function. Therefore, the stack pointer will point to the beginning of the activation record allocated for that specific function call. Now it's going to simply be a matter of interpreting that memory at that point in order to interact with the function instances, parameters, and local value variables. So with that, we'll move into just a couple of the next video will be pretty short and sweet. It's just some additional considerations. And then tomorrow we'll get into the stack a little bit more, and thereafter into dynamic memory.